Mhm.
All right, great. So I think I'm ready.
Okay, excellent.
So you want me to get going?
Sure, that'd be great.
Okay.
Thank you.
All right. Well, thanks everyone for joining. My name is Chris Mullen. I'm associate professor at this Department of Civil and Environmental Engineering at Virginia Tech. I'm part of a team of students and faculty and also part of the C-UAS team, including all of the industry sponsors. So the team is myself and Dan Stillwell. We're the primary PIs, and then Mayur Patil and Craig Woolsey from Aerospace Engineering at Virginia Tech are also involved, especially on the wind disturbance side of this project, which is focused on autopilot control for indoor and outdoor infrastructure inspection. And so we have outlined this project and the needs of this project are focused on being able to evaluate, explore, document the condition of civil engineering infrastructure. So bridges, buildings, roads, beaches, and even indoor environments as well. So the insides of containers, the insides of bridges, and thinking about how to utilize unmanned aircraft to provide a more automated, autonomous inspection platform. So there are lots of different directions we can go if we start talking about unmanned aircraft and inspection. So we can be thinking about the sensors, we can be thinking about the equipment itself, we can be thinking about the strategies for using these aircraft, managing the risk associated with these aircraft. And the direction that Dan and I went was just to focus primarily on the flight control. So we get a lot of feedback, or I was getting a lot of feedback from departments of transportations that one of their primary concerns about using unmanned aircraft in the vicinity of civil infrastructure is the concern of losing control of the unmanned aircraft as it's performing its duties. Those concerns were reiterated even recently. So we have Stantec representatives on this call, and they're thinking about how to incorporate unmanned aircraft into their typical inspection protocols. And one of the primary things that they're looking at is managing risk. So making sure that you don't lose control of the unmanned aircraft when it's flying around and near live traffic. And so the focus of this project is pinpointing flight control. So providing ultra reliable autopilot control. And then a secondary research goal is to demonstrate that with this precise autopilot control, that there are a lot of other ancillary benefits. And the one that we're focusing on is that the sensors that are actually recording the information that we need to develop and evaluate the condition of infrastructure are also enabled, or they become more effective. And I'll explain that a little bit later in the presentation. So this is the project vision slide that we presented last summer now, about a year ago, where we want to develop the tools that enable reliable flight and data collection in locations that are not typically accessible. The challenge with flying unmanned aircraft close to, even in an indoor environment, which Dan Dan Stillwell's our master student is going to talk about, Ben Straub. That's his focus during his master's research on the indoor, and then also documenting disturbances on the outdoor environment, and how those disturbances influence or how we can deal with those disturbances in a flight control setting. And so I would say that if we're thinking about the commercial solution, as I emphasized, the commercial solution for this is ultra-reliable unmanned aircraft infrastructure assessment platforms that the companies like Stantec or any of the other IAB members would want to offer and sell to this multi-billion-dollar inspection industry in the U.S. So our technical approach, I mean, the equipment that we have is generously provided by Dan Stillwell. He was the one who had already had these two unmanned aircraft in his lab and had already been working with them. And so these are the two guys that we're playing with over in this project. So one is the ducted fan, and then the other is a quad rotor. And the ducted fan has been the ducted fan is being utilized primarily for the indoor inspection, and the quadcopter is going to be utilized primarily for the outdoor inspection parts of this project. And our year one goals are really very simple and straightforward. We want to demonstrate that we can have robust autopilot or implement robust autopilot with disturbances near a wall or near a ceiling in an opening in an indoor environment, and then that we can handle disturbances and hold position at the exterior of a bridge. In this case, the bridge that we're actually going to discuss a little bit later, this is the picture of the actual bridge where we're going to fly the quadcopter. So managing or making sure that we can control the unmanned aircraft very precisely in an indoor and an outdoor environment. So you get the feeling that we're headed in two parallel but connected directions. And so we're going to present first now on Ben Straub's work on the indoor inspection with the ducted fan, and then I'll talk about the plan for the research field excursion to this Wolf Creek Bridge. This is a bridge that's in Southwest Virginia, where we're going to give our first attempt at some semi-autonomous flight with the quadcopter for the outdoor inspection. So Ben, I'm going to attempt to hand off the presentation slides to you so you can discuss more about your work.
There you go.
Let me see if I can find there it is.
Okay. There you go. Can you all see my screen now?
Yeah, I can see it.
Okay, great. So thanks, Dr. Moen, for that introduction there. So kind of what I wanted to talk about was just kind of what my initial progress has been on this project. Like you said, I'm one of Dr. Stillwell's grad students, and so I've been focused mostly on working with the ducted fan, which, like we said, we're envisioning that more for the indoor inspection than the outdoor, but a lot of it kind of overlaps with what we do on the quadcopters. Kind of the main points I want to hit with my section here is just some of the details about the ducted fan platform, which includes instrumentation and the dynamics and control of it, and then also just what are some of the issues we've encountered so far and what our current progress is. And this is kind of like our current state is that we have stable attitude control, and we still got some other control, outer loop control in progress, and I'll get more in detail about that. So why does this matter? How is this going towards our goal of indoor inspection? So kind of the high level steps towards indoor inspection that we kind of see is start out with some kind of orthodox, like traditional kind of approach with traditional instrumentation. And then from that, you build on the additional instrumentation that may be, let's say proximity sensors or distance sensors to sense a wall. Or maybe it's some kind of sensor that gives us some idea of disturbances around us, or just some kind of stochastic description of our current state. And then from there, you kind of build up into the agile control we're kind of envisioning. And so I've drawn here just kind of like a traditional control loop. And so you kind of start out with like a inner loop attitude control. And so that's just basic controlling your attitude, your roll, pitch, and yaw. And then outside of that, you kind of command a desired attitude with some outer loop controller. And so here I have a velocity controller to try to maintain some certain velocity. This could also be a position controller. And that's sort of a traditional approach. And that's what we're trying to really nail down right now with the ducted fan to get that working well. We've played around with some of the additional instrumentation, but this is kind of the main focus right now. So here's the actual ducted fan platform. Here's a nice picture of it. The idea is that there's a single propeller or a single rotor, and then there are 4 servo flaps underneath here that redirect that airflow to maintain the attitude. Here's a list of the sensors and instrumentation we have on it right now. So the main one is the Attitude and Heading Reference System, or AHRS. That gives us, it measures angular rates and linear acceleration and magnetic field strength. And then from those measurements, it'll also give us an estimated attitude and heading. We have a optical flow sensor that is basically a camera that looks down, and it also has an ultrasonic rangefinder on it to get an altitude measurement. And then using that, it'll look from like one frame of a picture to another, and it'll estimate a horizontal X and Y velocity, where X and Y are defined in like the horizontal plane and Z is down. And then we also have some infrared distance sensors. And so we have one mounted facing down to just give us another altitude estimate. But we can also put others around the edge. And we've done some testing with this for sensing walls or obstacles nearby. And then also I've included the electronic speed controller on this list because we get RPM feedback from that. So it tells us exactly how fast the propeller is spinning. And then as for the control electronics, we have 2 microcontrollers on there. One we kind of refer to as like the main control board or the flight control board. It's just an ARM microcontroller, but it was kind of specially designed, intended for autopilot. And so it's what handles actually calculating all the control signals, control values, and driving the servos. And it also handles receiving the RC input. So I can manually control this from a controller when I'm just testing stuff out. And then it also reads the ESC. And the other board that we have, we kind of had to use because the main one didn't have enough ports for everything. And so this basically handles reading all the sensors. So we call it the sensor board. But what it does is it'll read the AHRS and the optical flow and the IR sensors, and it'll do some filtering, and it has to do some calculation in there. And then it will send it all to the control board, and it'll also log everything. So we have fully logged data from everything. We can look at it after the fact, and it's pretty nice to look at. So. And then here's just kind of a quick block diagram showing how everything's connected, in case you want to see that. So as you can see, you have kind of the main like actuators connected to the flight control board, as well as the RC input, and then the sensor board kind of connects to all the sensors, everything else. So going into some of the issues we've seen so far, the big one has been issues related to vibration. And so this is our AHRS sensor, and we've had a lot of issues with it. So the way it works internally is it has an extended Kalman filter that takes all of its measurements and estimates the attitude. So this particular brand of AHRS has a sort of proprietary algorithm inside of it that will attempt to tune the parameters of that EKF, and it'll tune like uncertainties and things like that. Turns out it does not behave well under the kind of profile of vibrations we see, and so that was causing a lot of issues. And so this graph over here, I recorded this data while actually like holding the chassis on the ground, and then ramping up the propeller. And so you would expect the roll and pitch and yaw all to stay like at 0 degrees. But because of the like broken tuning issue, you can see this is the roll in blue here is drifting off to like 30 degrees or worse. So that's pretty bad. And then another issue that you can kind of see in this graph is the acceleration and the angular rates are experiencing some really high amplitude noise, which is also an issue for control. So the way we kind of tackled these issues, first of all, we did some like vibration isolation mounting, which I tried to capture in this picture, but it's kind of hard to see everything that's going on. It's kind of just like held up against here with a zip tie, but it's got some sorbethane foam around the edges, kind of lightly touching. But then the main thing that's you can't see is underneath here. It's cushioned something called a moon gel, which I don't know if any of you are musicians, but a moon gel is something that drummers actually use to dampen vibrations on snare drums. So found out about this and heard that it worked pretty well, so tried it out, and it did help a lot. Another thing we did was turning off the EKF tuning, that proprietary algorithm that they have running inside there. There's a way to configure it so you can actually turn that off, and that helped out. And then just for the actual noise, we had to increase some of the filtering just to get a more filtered reading. And then another issue we had was, even with all that, we were still seeing the yaw drift like really badly. And so the way we got around that was just looking at the raw magnetometer data and doing a manual calculation of yaw. And so this is the same kind of test that I showed in the previous slide, but with all those changes in place. And so you can see it performs a lot better. You're not seeing the drifting anymore, and the amplitude of this noise is a lot lower than it was before. Similarly, with optical flow, we ran into some issues. One thing that helped with that was, again, just vibration isolation. Another issue was that the firmware provided by the Pixhawk, which is who makes the sensor, doesn't perform very well, especially at low altitudes. And so the main thing to get from this plot here is just that when we were performing at like a low altitude of, say, like 0.5 meter off the ground, which would be pretty typical for indoor kind of things, it just doesn't want to give readings. If it thinks the quality is too low, it will just tell you nothing. And so the point here is that there's just not a lot of readings coming in. This is in seconds, so this is a relatively long amount of time to be getting no readings from it. Luckily, we found somebody who made open source firmware that improved a lot of these issues and gave much more consistent readings, and you'll see that on the next slide. And then the other thing was doing some complementary filtering with acceleration, which I show here. So the blue here is the optical flow measurement we get with this new firmware. And so you can see it's still a little bit noisy. And so we also have the acceleration. So the red line is what you would get if you were only integrating acceleration. And so obviously you'd see a lot of drift with that. But we used a complementary filter to combine the two and got a much nicer estimate, which is shown in yellow there. We did a similar sort of thing with the altitude. First, we had several different sensors that gave us an estimate of altitude. So we had the IR sensor facing downward. We had the sonar sensor also facing downward, which gives us a further range, but a bit of a noisier estimate. And then we also have a barometer measurement, which is not real accurate, but obviously can go much higher. It doesn't have to be pointed at the ground or anything. And so first off, we just combine all three of those based on different thresholds. So each sensor has a certain operating range that it performs best at least for the IR and the sonar. And so depending on how high we think we are, we weight one more heavily than the other, or sometimes just completely ignore a certain sensor if it's outside of its ideal operating range. But then we also do complementary filtering, again, with the Z acceleration. And so that gives us a complementary filtered estimate, which is in blue here. And then we also happen to get a Z velocity estimate from this, which seems to work reasonably well. And so with all those measurements, to actually control the vehicle, we need to do some kind of dynamics modeling. And so to do this, we just used kind of first principles to develop a parameterized equation for the dynamics. So this is just like, looking at physically what's happening. And so you can see there's 5 terms here. This first one just comes from X and Y velocity. So moving horizontally, there'll be air flowing over the lip of the duct, which will cause a moment one way or another. This C2 term comes from the actual servo inputs. And so originally I thought this would just be kind of like a linear relationship to the U is the angle of the flap, and this delta is some offset. Turned out to be not quite a linear relationship, and I'll get into that more in the next slide. The third term is a gyroscopic effect from the propeller spinning while the body actually leans one way or another, causes like a moment along the other axis. And then this is just sort of a general like angular rate damping kind of term. And then this last C5 term is also a gyroscopic effect of the whole body turning while it leans one way or another. That term turned out to be turned out to have not a lot of effect on it. And so I ended up leaving that out in a lot of my modeling. And then the second equation is just the general, the change in Euler angles relating to the actual body angular rates. And that's a pretty standard thing.
Ben, can I ask
Yes.
you a question?
Absolutely.
So for those of us who aren't used to looking at this equation, so P
Yes.
and Q, what are they?
Oh, sorry. Yeah, P and Q are the body angular rates. So P would be the change of angle around the x-axis, Q would be around the y-axis, and then R, which shows up here also, R is the angular rate about the z-axis, so like the turning yaw axis.
Okay, I get it. So there's 3 degrees of freedom here that you're treating, I think, then.
Yeah.
Okay.
Okay, so with these equations, basically the idea was to gather a bunch of data, trying to do some test flights, and then using that data to try to estimate the unknown parameters by trying to fit some kind of minimum squared difference. And I tried 2 different approaches with that. One was to actually do like a nonlinear ODE simulation to try to simulate these equations with some estimate of the parameters, and then to tune that estimate by comparing the ODE simulation to the recorded angular rates. That turned out to be a pretty slow method because doing the actual simulation took a while. So what turned out to be a much faster method, but seems to perform about as well, is just estimating the angular accelerations directly from the data by looking at the recorded angular rates, and then comparing the predicted, from this equation, the predicted angular acceleration to the estimated from the data, and doing a minimum squared difference of that. Looking at that input function that I was talking about on the previous slide. So originally, like I said, I kind of estimated it to just be like a linear kind of effect. And so that's what I did with some of my earlier modeling. But then I had a chance to do some testing with a force torque sensor, mounting the actual chassis on a sensor and getting to look at some of the forces on it. and found out that from this graph, this is the flap angle of the servo for some direction that may be roll or pitch, and then looking at the forces generated from that. And so it actually turned out to be more of a sinusoidal kind of thing. And so now I'm estimating it with this sine function here. And that performs a lot better, it seems. Yes.
Ben, again, so is that's the force of the duct, the motor? So
this was the like lateral, like sideways, like X or Y force on the, so this was on the actual sensor. So really what I care about is how the flap angle corresponds to a moment about the body, about the center of gravity.
Mm-hmm.
But the way the sensor was mounted, it was mounted at the bottom, whereas it wasn't mounted at the center of gravity. So when I see like a lateral force on that sensor, that directly relates to a moment about the center of gravity. There's just some distance between where the sensor was mounted and the center of gravity, and then the moment of inertia would factor into that too. But that's why in the previous equation I just have this C2 that kind of absorbs all of the moment of inertia and the distance from center of gravity and all those terms, all just combined into one kind of constant.
I was just trying to figure out, but is that like the force, where's that force coming from? Is that the wind force? Is that an external force, or is that a force generated by the... So
as the motor pushes air through the duct, it hits the servos, it hits the flaps, and if the flaps are at an angle, then the air bounces off and it will cause a force in the other.
So it's a propulsion force.
Mm-hmm.
Okay, got it.
So to actually come up with a controller for this, first thing was to linearize the attitude dynamics. So the equations I had earlier were nonlinear equations. So I had to linearize about some equilibrium operating position, which was just upright, hover kind of mode. Also with that function of input, I went ahead and used the transformed input. So I treated this whole equation as kind of like a V, like a new input. And so when I'm actually calculating the control values on the controller, it calculates it in this transformed space, and then it just does the inverse of that sinusoidal function to transform that back to what the actual servo value should be. The actual controller design is LQR controller design, which stands for linear quadratic regulator. This is just a controller design where you give it the linearized dynamics and you specify some kind of weighting on, how much you value, like weights on the inputs and weights on the states. If you value air in the roll and pitch more than yaw, then you can specify that. And then after you give it all the weights, it comes up with some optimal controller design that will attempt to minimize those weighted values. So I have here a video of me running the ducted fan. So all I'm using on there right now is you'll just see attitude control. And so it'll just be trying to stay level. And I'm holding a controller right now, or in the video I am, and I'm just manually controlling the roll and pitch with a joystick. It tends to want to drift off to one side or another, so I'm having to kind of fight it, and that's why you see some of these jerks where it will kind of drift off to the right, and then I'll kind of jerk it back to the left to try to maintain kind of a center. Part of that's just that I'm not a very good pilot. And then also another thing, I don't have altitude control running here either. And so I'm trying to lift it up off of its tether. Like it's tied to a point up and towards the ceiling. And so as I lift it off, once it starts to lift up, I'll try to turn the the RPM down a little bit, and then it will kind of fall sometimes. So you'll see some of that too. But all in all, it looks pretty good. It's not doing anything that I wouldn't expect, and so that's good. Here's the actual data from that run, and so you can see the RPM plotted in the top stays pretty constant, and then the angles you can see also stay pretty close to zero. You see some of these spikes where I kind of jerk the controller a little bit. And also you can kind of see the servo values. So this time is in seconds. So relatively long times, and you're not seeing a lot of too much jerking or chattering in the servos. So that's a good sign. And also just kind of the point of this plot was just to kind of show I can collect data while it's running, and I can plot everything. So.
But Ben, the attitude, you said it was attitude control only, right? You were trying to maintain a certain. So
yeah, just to maintain zero angle, I guess.
Yes. Okay. Zero. So you want zero angle.
Except I can also I was also manually controlling what the desired angle was during that, and so if I'm holding left on the joystick, it may be trying to maintain some negative roll angle or something.
I see. So is it just the blue line then that you're trying to maintain as zero?
It's all three. So
it's all three. So you're trying to get all three of those to zero, but sometimes sometimes it was you were pushing the joystick so that it was supposed to be at a certain, like right there is maybe supposed to be at 20 degrees. The yellow, the yaw.
Yeah. So the yaw controller isn't real aggressive, just because I don't care a whole lot about the yaw. The yaw is not gonna make it go too crazy, and so I had kind of the yaw gains turned down a bit, because yaw is just kind of spinning around a little bit.
All right, but overall, I mean, if you look at if you care about the blue and the red lines, then you're getting pretty close to zero.
Mm-hmm.
Yeah, not bad. Okay, cool.
Yeah. And so then some of the other things I'm working on, I already have. So I've shown you the altitude measurements and the filtering estimates of that. So I've got that in working. And I've already implemented kind of an outer loop, just basic PID control to go around that to command some propeller speed. And that's already been implemented and tested a little bit, but really it just needs more tuning right now because it's just difficult with space constraints. I don't have a lot of wiggle room to move it up and down in a limited space. So I'm still working on that. And then also position and velocity control is still in progress. Again, I already have outer loop PID control that will command an attitude to the inner loop. And I'm using those filtered velocity estimates I showed you. Right now, it'll kind of maintain its place a little bit, but it's really wiggly. It'll go back and forth. So I think that just needs more tuning. Also,
Ben,
yes.
Ben, how did you address the non-minimum phase from the tilt sensors? It looks like you have the sensors below the CG, right? And then and so you're using linear control methods, but you didn't mention that you had any issues with that.
Are you talking about for the attitude sensors, or?
Yes.
I mean, I haven't had issues with that.
Well, good.
I mean, yeah.
Good. Let me put it this way. We have a lot of similar issues to resolve that you seem to be resolving, including the lack of space, and we use professional terms like wiggliness as well. So.
Yeah. I have had a little issue with the velocity being non-minimum phase and the position. I'm hoping I can just get rid of that with just more tuning. Yeah, because there's the issue of, if you want to move to the left, the servos kind of, to move to the left, you have to lean left, but to do that, the servos kind of push it to the right first.
Yep, exactly. Yeah, and there are definitely some nice tricks to deal with that.
Mm-hmm. Yeah, and so that part's still kind of in progress. But hopefully it gets tackled soon. So then another thing that I've kind of done in the past is I have IR sensors on like the edges to see the distance to the wall. And I've tried to maintain a distance to the wall. And I've done this on the quadcopter. I haven't tried it on the ducted fan yet. But I had issues with that too, where I think the IR sensor has to be pretty close to the wall to see. It has a range of about 1.5 meters. And so once it starts getting really close to the wall, I do start running into some of the effects of just being that close to a wall. It changes the dynamics a bit. And it either wants to pull it in towards the wall, and then the controller kind of over adjusts for that and throws it out away from the wall, or that kind of thing. But one of the next steps I'm looking at doing is to kind of combine. So this past experiment was done using only the IR sensor. I didn't have any of the velocity sensing working at that point. So I'm thinking if I combine some of the IR sensor and the velocity estimates, then maybe I can get a better controller out of that. So that's some of what I'll be looking at in the future. But I think that covers it for my slides. So unless there's any other questions, turn it back over to Chris.
Yeah, are there any other questions for Ben? I have about maybe 10 more minutes of slides. Or comments even? Questions or comments?
Okay.
This is Adela from Stantec. When we send staff into a steel box girder, for instance, and we're looking at welds, I guess, we're usually stationary for a while. So we'll crawl through a diaphragm, and then we'll kind of sit down inside the box, and then we start, inspecting the welds. It seems like that inducted fan, the way it's kind of moving around, I'm not so sure it needs to be flying the whole time. Why can't it fly through the diaphragm or something like that, or through the hole, and then just go in there and kind of sit itself down, and then you just have a 360-degree camera mounted on that thing, or a camera that has a gimbal that does 360 degrees and goes up and down and left and right and all that stuff, and then you start scanning the inside of the box from there, and then when you need to look somewhere else, then you fly the thing to another location to where you can see it. And so it's kind of like you're using the flight to kind of move yourself through the box, but you may not necessarily need to have it flying the whole time, is my point.
Mm-hmm. Yeah, that may be a good point. We have, you can see this mount in the picture here that we're kind of leaving there to mount a camera or something. So it would be pretty easy to just put something like that, like a 360-degree camera or a gimbal mount that can just spin around. So that's a good point.
Well, to Ryan's point also, in terms of sitting it down at a specific point on the bridge, not necessarily, we're not going to have a floor for this to land on underneath the bridge all the time. One thing that I was thinking is that if you could somehow activate a magnet that would, if you have a steel bridge, this could attach to the web of a girder and run that 360-degree camera, and then deactivate that magnet the moment you want to start moving again. So that's just an idea also.
That's a cool idea.
Well, Leo, the ducted fan is just for going inside confined spaces, I believe Chris said, and then the quad rotor was for doing bridges. So the ducted fan that you're seeing here is only for going inside, and I think you would have a floor.
Got it. Okay. Also, I have a question. Ben, you mentioned you have limited test space right now.
Mm-hmm.
Is there is that going to change for you anytime soon, or why do you have a limited test space?
So I've been doing all my flight tests in just like a like a small office kind of thing. Like there's nobody working in there, but it is. I mean, it's what I have to work with right now. There is another professor here who has said that I can use his flight lab. He works upstairs from me, but his flight lab is not ready yet, and so hopefully in the somewhat near future, I'll be able to use that test space, and it should be a lot more useful.
Okay.
And I guess another issue is I haven't been able to like fly outside. Might also be a potential test space where there's lots of open room. It's just that so there's regulations and stuff with that, and so we've just been trying to stay indoors so that we don't have to deal with all that right now.
Great. Thanks, Ben. That was good stuff. Can you send the host back over to me? I think maybe you're the only. You just did it?
Yes. Okay. Yeah. You should be host now.
All right. Cool.
Good job. Good job, though. That was a good presentation, Ben. Thank you.
Yep. Thanks.
All right. So you can see that we have a solid team with a lot of expertise in flight control. Definitely a great presentation, Ben. And so now what we're trying to do is to take some of that out to an actual bridge. And so we have that bridge, and we're headed out there soon to do some very preliminary, I'm calling it a research excursion, to fly the quadcopter, not Ben's ducted fan, but fly a quadcopter at this bridge and try to measure something. So do some condition assessment with some autopilot control. This bridge is located in Southwest Virginia. It's my PhD student and I have worked on it for other reasons. For the Virginia Department of Transportation recently. It was just reconstructed. And so the cool thing is that we have, first of all, it's a pretty rare thing that we get access, VDOT access to a bridge. And so that was the first hurdle that we cleared. And the plan is to focus primarily on this wing wall. So for those of you who aren't bridge engineers, which is probably most of you on this call, there are lots of different pieces of a bridge, but there's this wall that holds it's pretty much a retaining wall that holds the approach when you're driving up to the bridge, holds all of the earth so that the approach doesn't collapse. And so we're going to focus on flying a quadcopter with a proximity sensor and GPS next to this wing wall. So trying to keep it very simple, just taking the unmanned aircraft and flying it up and down against this wall, pretty much. So
Bruce, we can't see your screen.
Oh, really? Oh, here. Sorry. That's thank you for letting me know. Here. I guess I should have shared my screen. Oh, there. I didn't share my screen. Sorry. There we go. So now, here you go. Oh, now I got to figure out which window. There it is. Sorry, so I'll just let you digest this a little bit. You can see that the bridge is pretty much out in the middle of nowhere, which helps us a little bit, I think. VDOT was not too concerned about us playing around out here.
Chris, what's the schedule for this field test?
It's coming up in one slide, Leo.
Okay.
Something else I should mention is that the sensor that we're going to be flying is, so we have the capability to create 3D models of anything, really, with videos or still images. And so that's part of it also, is that when we're flying the unmanned aircraft, we're going to be taking and creating 3D models of portions of this wing wall. And that's the integration of the flight control with the sensors. All right, so here are the goals for this part. So Leo, here it is. There's the date, June 30th, 2016. I think it's a Thursday. And we're going to start trying to bring the autopilot control work that Ben has been working on and that Dan has been plugging away at even for a longer time from the lab to the field. We have the advantage of DOT interest, and we want to highlight the benefits of autopilot control to them and to the, I guess, the infrastructure community. We also want to collect field wind disturbance data to support our autopilot development. So we're going to be measuring wind speed and direction around the bridge. And also we want to develop relationships so in this case, we're working with the Mid-Atlantic Aviation Partnership and to obtain our COA for this project. And so we just wanted to go through the procedure of getting a COA because at least for me, I'd never done it before. So, yep. So it's as simple as this: document the condition of a wing wall with the quadcopter. You'll notice that there's certain features on the wing wall, and so we're going to focus on just trying to accurately identify and measure a few of these features. We haven't selected the exact features, but there are formwork marks. So like this was a plywood 4x8 sheet of plywood, and there are ways that they anchor that plywood, and so we can measure this circular indentation, for example, and then try to fly the quadcopter at that location, at that elevation, and collect information with video sensors or a video sensor, and then try to compare it to measurements. So the quadcopter we're using will have GPS and the IR proximity sensor integrated with the autopilot control. And we're also installing some Raspberry Pi ribbon cameras, sensors, so video camera sensors, 5 megapixel, that will be collecting the data that we can use for the measurements of the features that we're looking at on the wing wall. It's I emphasize the important. I mean, this is we're trying to keep the experiment or excursion very simple, but overall, from what I'm seeing in the inspection community, at least bridge inspection community using unmanned aircraft, the location, like the proximity that they can get to the actual bridge is still pretty far. It can be up to 7-8 meters. And the problem with that is that they can't get the resolution and the detail they want to look at. They want to look for cracks and for rust and corrosion and weird buckling, and it's hard to do that when you're 7 meters away. And so a big advantage of this autopilot control is being able to get closer. And so that's one of the focuses for us, is that we're going to try to obviously do much better than 7 meters on this wing wall. Yeah, I put in this slide, but maybe we don't need to go over it. It's obvious. If you get closer with the same number of pixels, then you have more accuracy in the characterization, and if you're trying to measure something. So I just put in. So this is the COA plan that we have with the Mid-Atlantic Aviation Partnership. So they'll do airworthiness studies. They'll have a pilot out there with us for 8 hours during that day on June 30th. You can see that this is not cheap. So it's $2,500 for us to play around out there for the day. But I mean, that's why we have the support of the IAB and funds for this project, is to start getting out there. Yep. So the field study is that we're just going to be measuring wind speed direction at a few different locations, thinking about maybe even how the wind speed and direction is varying along the height, identifying 2 or 3 features on the wing wall, and then carefully documenting those feature characteristics, dimensions, and then setting the unmanned aircraft with the GPS location and recording the video of the features, along with all all of the goodies that Ben was talking about that he can grab as the platform is flying, and then also use the IR proximity sensor, set it like, let's set it like 1 meter from this wall, and just let it try to hold itself there. And we'll take some sensor measurements, and then again, evaluate the accuracy of the features one by one. We're looking at this circular feature and this crack, and maybe there's a crack here, and maybe there's something else here. So you get the idea that we're trying to cover a lot of ground here, where we're measuring the wind and trying to measure even wind disturbance. We're trying to evaluate the flight control with GPS and with the proximity sensor, and we're also trying to understand the influence of all of that on the accuracy of the measurements that we actually want to make for the inspection. And post-processing, wind models, variation of disturbances along the height, the digital state models of the wing wall, and documenting dimensional accuracy, and then evaluate stability accuracy of the different autopilot GPS hold and IR proximity hold. And the year one deliverables for this project, I mean, you can see we've made a lot of progress. We're ready to crank here in the next month to gather a bunch of outdoor data, and then so we'll have Ben's thesis, which is advancing indoor autopilot, where the outdoor work will be recorded in a transportation research board paper. So this is, for those of you who don't know, this is a conference of 15,000 bridge and infrastructure engineers that that come together in January every January in Washington, D.C. And so this work will be presented there. And then the third thing that we'll be working on in the last half of this year is the wind models. So we're going to have a bunch of wind data, and we want to work with Meyer and Craig Woolsey to think about how we can use those wind models to fine-tune the autopilots and then thinking about next year. So you can see we've made the first baby step where we've gotten out in the field. We have some wind data. Ben has some nice control algorithms. We're using proximity sensors. So next year we would love to take the next step, where we do version 2.0 of the autopilot. So maybe a DOT, we find a different DOT, and they're even more integrated into the process. So we're thinking about maybe even flying it near or over live traffic to do some more complicated inspection than just flying it up and down on a wing wall. So we are seeing year two is actually just like going through these steps again, but just making a leap from what we learned from this year. So that's the presentation. And so we have just 3 minutes, so apologies for that. But if there are any comments, I'd be happy to take them now.
Hey, Chris, I think I missed this. This is Ryan Nadaluk. When are you going? You had a lot of good stuff at that Wolf Creek Bridge. You already went out there, or did you already take a bunch of? When is that happening?
So we've been out there a few times for other research reasons, but we're going out there on June 30th to do this unmanned aircraft research excursion.
Oh, that's cool. Okay, June 30th. Got it.
Yep.
The Colorado DOT, and I'm in Denver here. I'm talking to them. They're excited about this, and we have some really remote bridges, and so I want to know. Yeah, I'm excited to hear how it all goes and everything.
So maybe next year, we can do the version 2.0 at a Colorado bridge.
Yeah, that sounds great. We'll start working on that with you, Leo, and Dan. That sounds great.
Chris, can we get a copy of this presentation, Ryan and I?
Sure. I'm actually recording this too, so.
Fantastic!
We'll have the YouTube video in an hour.
Great.
Hey,
yeah, we'll show
Chris,
it.
Is there any way you can put modify just a little bit your plan and put an IR camera on there as well, like an infrared thermal camera on there to see if you can see like delaminations or cracks or anything, or
That's,
or
that's
is
too
your,
big. That's too many that's too many baby steps for us. We're
okay,
just
I got it.
like next year. I love it that you're thinking about it, but I mean, we're pretty locked in right now on and time and effort and everything. So, but next
Okay.
year for sure. Let's think about it.
Those little holes that you're looking at on the that piece of plywood, those are called form ties.
Yes, form ties. I knew that back in my days as a bridge engineer. I knew what they were called, but it's been a while. Thank you.
Yeah, exactly.
Thank you. Whew.
Thanks so much, Chris. You did great.
All right. Anything else? Any other comments before we sign off?
No, thank you. Appreciate it.
Okay, everyone.
Looking great. Thanks, everybody.
Take care.